Welcome to the deep dive. Today, we're embarking on, well, a bit of a cosmic adventure, really.
Sounds exciting.
We're exploring how the Gaia space mission is fundamentally changing how we see the solar system.
A big topic.
Huge. And for you, our listener, if you're curious about this stuff, this is your streamlined journey. We're giving you a shortcut.
Yeah, cutting through the noise.
We've basically mined the data, focusing especially on one key document, Perryman Gaia 064.pdf, to pull out the really core insights for you.
Good source.
Our mission today, let's go beyond the standard textbook facts. We want to unpack the really significant discoveries Gaia's making right in our own celestial neighborhood.
Absolutely. And it's worth remembering, isn't it, that even before Gaia, the idea of observing the solar system from space, well, it held immense promise.
Oh, definitely. Hipparcos, its predecessor.
Right, Hipparcos.
Yeah.
It only gave us a relatively small sample looking back, but it really showed what was possible, free from Earth's blurry atmosphere.
Exactly. I mean, just 48 asteroids charted. And a few bright moons like Europa, Titan, Iapetus, Uranus and Neptune, Ganymede, Callisto, they popped up in the Tycho catalog. But that was, well, more focused on stars anyway.
It really was. And the limitations back then seem almost quaint now, don't they?
They do. Objects had to be pre-selected. They had to be bright enough.
And not too close to a planet, or, you'd just lose them in the glare.
Yeah.
Scattered light was a real problem.
Totally.
So for Hipparcos, the main goals with those solar system bodies were really about establishing a more precise cosmic map, a dynamical reference frame, technically.
Right, and getting some early estimates of their masses
Why?
by watching how they sort of tugged on each other gravitationally.
Exactly that. Plus some, basic inferences about their composition from their photometry, their brightness. It really did lay the groundwork, proving how valuable that stable, space-based viewpoint could be.
Okay, so let's jump ahead. Turn of the millennium, the concept phase for Gaia. Even back then, the predicted leap in capability, it was just astonishing.
It really was. That concept and technology study you mentioned, the review, it foresaw this incredibly deep, uniform survey of minor planets, down to magnitude 20, maybe 21.
Which is incredibly faint. That just blows the doors open for studying things like near-Earth asteroids.
The ones that could potentially cross our path.
Yeah, and also those really distant icy bodies way out in the Kuiper Belt.
And what's so fascinating, I think, is why this deep survey matters so much. These smaller objects, they're like frozen relics, aren't they?
Leftovers from the very beginning.
Exactly, from the protosolar nebula, that cloud of gas and dust that formed everything. So by meticulously studying their movements, their properties, what they're made of,
You get fundamental clues about how the whole solar system formed and evolved over billions of years.
precisely.
And the sheer numbers they were predicting back then were just wild. Over 100,000 new discoveries.
Including things like the inner Trojans,
Yeah.
those asteroids kind of hiding near Jupiter's orbit.
Right, sharing its orbit, but leading or trailing. And plus, the idea of getting these incredibly precise orbits pinned down by years and years of watching them again and again.
Okay, so fast forward again. Let's talk about the data we've actually received so far. Gaia Data Release 2, that was April 2018.
Our first real taste, yeah.
It gave us that initial info on, what was it, around 14,000 asteroids from the first 22 months or so.
That's right. And then early data release 3 didn't really add much on the solar system front.
No, it didn't. But the one we were all really waiting for was Gaia DR3, expected around mid-2022.
And DR3 sounds like it's the real game changer. We're talking detailed measurements, astrometry, and some orbits for maybe 150,000 asteroids.
A huge jump.
But get this, an unprecedented spectral survey for over 60,000 of them. So not just where they are, but getting a real sense of their makeup.
That's the key, isn't it? That spectral information unlocks a whole new level. It lets you do taxonomic classification.
Sorting them into different types based on how they reflect light.
Exactly. And that allows for much more sophisticated studies of, well, how these different populations move, how they interact, the dynamics of it all.
And even with just that earlier DR2 data, we're already seeing these really exciting hints of Gaia's power.
Absolutely. For near-Earth asteroids, for example, the positional accuracy was already getting close to radar ranging.
Which is the gold standard, really.
It is. And there's this dedicated follow-up network, about 100 observers or so, chasing down Gaia's initial alerts, leading to even better orbits.
So connecting the dots, the combination of Gaia's super precise asteroid orbits and its incredible star catalog, that's having a massive impact on stellar occultations.
Huge impact. Those events where an asteroid passes right in front of a distant star.
Making the star just blink out for a moment.
Yeah. And those fleeting eclipses, as you call them, they're proving incredibly informative.
We've seen studies using them for minor planet Carnegie back in 2016.
And the ringed centaur, Chariklo, in 2017. Even Neptune's moon Triton in 2018.
It's like using the asteroids themselves as tiny probes.
It really is. And what's truly remarkable now is that the timing of these occultations is measured so precisely.
That it's sensitive to the asteroid's own details, like its size and shape.
Exactly. Its exact size, its 3D shape, even how fast it's spinning. And then, wonderfully, those occultations themselves help us refine those very properties.
It's a feedback loop.
A beautiful scientific feedback loop, yeah. Observation and analysis feeding each other.
And we started getting sneak peeks of what DR3 held. Paulo Tonga highlighted detecting the Yarkovsky acceleration
Yes.
in 20 newly found asteroids. Now, this is fascinating stuff. It's this tiny, tiny push.
Almost imperceptible.
From how a small rotating body absorbs sunlight unevenly and then radiates heat back out.
Yeah, thermal radiation.
But over millions, billions of years, that subtle force can actually change an asteroid's orbit. It's not just gravity pulling the strings.
It's a really subtle but crucial effect for understanding long-term evolution. And then there was the photocentric wobble of asteroid 4337 Arecibo.
The first one found to have its own moon just through occultations.
That's the one. Another great example of Gaia picking up these tiny orbital dances that were just incredibly hard to see before.
Plus, there was work by Delbo and others showing that the color information Gaia gets from its BP and RP photometers.
The blue and red prism data.
That this will let scientists map out the composition gradient across the main asteroid belt, even for smaller objects.
So like getting a broad chemical survey of that whole region between Mars and Jupiter.
Yeah. Exactly.
Now, it's important to realize that dealing with solar system objects in Gaia data, it throws up unique challenges.
Because they move, right, unlike the stars, relatively speaking.
Exactly. They have significant proper motions, noticeable movement across the sky. That means the data processing has to be way more sophisticated than for the fixed stars.
Right, like trying to photograph a speeding car versus a mountain peak, different ballgame.
Totally different.
Okay, so how is this huge data processing job actually handled? It sounds incredibly complex.
It is a massive undertaking. The Gaia Data Processing and Analysis Consortium, DPAC, uses this distributed system. Think of it like a central hub with spokes going out to specialized teams.
Okay.
The raw data generally goes first to ESAC, the European Space Astronomy Center in Madrid. They do the initial heavy lifting source matching, the core astrometric solution, AGIS.
AGIS, the Astrometric Global Iterative Solution.
That's the one. Then various coordination units, or CUs, based at different research centers across Europe, they take that foundational data and do the specialized deep dive analyses.
And one of those CUs is dedicated just to solar system objects.
Precisely. Coordination Unit 4, CU4. That's the team responsible for solar system objects, led by Paulo Tonga in Nice.
Ah, the name we heard earlier.
Yeah. His team's about 25 people or so with big computational help from CNES, the French space agency, in Toulouse.
Still seems like a small team for such a huge task.
It does, but it also shows the interconnectedness. I mean, get this. The paper describing the DR2 solar system results had something like 450 authors.
Wow, 450.
Yeah. It just highlights how collaborative these big science missions are. It takes a village, or maybe a continent in this case.
That's incredible collaboration. So looking ahead, by the time Gaia finishes its mission, it's expected to have observed something like 350,000 solar system objects.
That's the prediction, and many of them completely new discoveries. Plus, observing them multiple times over the years, it's just a staggering amount of data.
So for DR2, that initial set of about 14,000 known asteroids, how were they chosen?
They were carefully selected to represent the main dynamical classes, the main types of orbits we see.
Okay, so main belt asteroids.
Yep, between Mars and Jupiter. Near-Earth objects, the NEOs, Jupiter Trojans, sharing Jupiter's path,
Right.
and the distant trans-Neptunian objects, the TNOs.
Got it, so a good spread.
A good spread. And these already had pretty well-known orbits, which helped in identifying them in the early Gaia data. Those objects accounted for nearly 300,000 transits across Gaia's detectors in just the first 22 months. Almost 2 million individual CCD observations.
And the way Gaia scans the sky matters too, doesn't it? It doesn't look everywhere all the time.
No, the scanning law means it mainly observes objects within a certain angular distance from the sun, between 45 and 135 degrees solar elongation.
But within that wide band, it covers the whole sky over time.
Exactly. Now, the basic processing for these moving objects is actually quite similar conceptually to the stars.
Okay.
They use that big AGIS solution, the overall sky map, to convert the raw detector signals, the focal plane coordinates, into precise sky coordinates.
And that involves some seriously complex math, right? Going from the satellite's own frame of reference.
All the way to the barycentric reference system, the solar system's center of mass, and, crucially, accounting for relativistic effects like the bending of starlight by the sun's gravity.
Einstein's general relativity playing a role even here.
Absolutely. You have to account for it at this precision.
And the result, what kind of accuracy are we talking about?
It's phenomenal. For the brighter objects, say G magnitude less than 17.5, the accuracy for a single observation is below 1 milliarc second.
Which is tiny, like seeing a coin hundreds of kilometers away.
Something like that, yeah. Even for the faintest ones Gaia sees, around G magnitude 20.5, it's still only 2 to 5 milliarc seconds.
Incredible.
Now, a single transit is technically more accurate along the scanning direction than across it, so it's sort of one-dimensional accuracy.
Good.
Because Gaia scans in different directions over time, that averages out beautifully across multiple observations. The scanning pattern imprint gets smoothed out.
Okay, that makes sense. Now, what about measuring brightness, the photometry? Does the movement cause problems there too?
It does, yes. Because an asteroid can be moving quite fast relative to the background stars. During that short exposure time on each CCD, just 4.4 seconds, its image can actually smear across several pixels. A motion of about 13.6 milliarc seconds per second means it shifts by a whole pixel doing one exposure.
So you get a little streak instead of a dot.
Essentially, yes. And that smearing has to be carefully modeled and corrected to get accurate brightness measurements. It complicates the photometry.
Right. And then finally, turning all these precise positions into actual orbits. How's that done?
They use a standard but powerful technique called least squares adjustment, or fitting.
Huh.
You start with the best previously known orbit elements.
Kind of initial guess?
An initial guess, yeah.
Yeah.
And then you use Gaia's observations to refine it, crucially factoring in all the gravitational pulls, the sun, all the major planets, our moon, Pluto, even the 16 most massive asteroids in the main belt.
Wow, they include the biggest asteroids too.
They have to for this level of accuracy. Their gravity matters. They use the JPL D431 planetary ephemerides as the background model for all those gravitational effects. It's this intricate gravitational dance they're modeling.
And there's that diagram you mentioned, plotting orbital eccentricity, how stretched out the orbit is against the semi-major axis, the average distance from the sun.
Yeah, for the 14,099 objects in DR2, it really paints a clear picture, doesn't it?
It does. You can visually see the different populations pop out. The near-Earth asteroids with their often more eccentric orbits.
Crossing planetary paths.
The main belt asteroids mostly cluster together, including the Jupiter Trojans in their specific locations.
And then the very distant TNOs way out on the edge, like a map of the solar system's architecture.
And looking forward, the improvements are just going to keep coming. Studies suggest that with a 5-year Gaia mission,
which it has already exceeded.
Right. The knowledge of typical main belt asteroid orbits improves by nearly a factor of 10 compared to pre-Gaia ground-based data.
A 10-fold improvement. And if Gaia operates for 10 years, which it looks like it might,
that improvement could jump to around a factor of 20.
It's just, abundantly clear. The sheer volume and the unprecedented accuracy of Gaia's measurements will vastly outperform anything we could do from the ground alone, even if we track these things for decades more.
It's a fundamental shift.
A complete transformation in our ability to map out the dynamics of our solar system.
So let's try and wrap this up. This deep dive into Gaia and the solar system, it really shows a mission that's truly revolutionizing how we see our cosmic backyard, doesn't it?
Absolutely. We're getting this immense flood of incredibly precise data, and it's fundamentally reshaping our understanding of everything. Dynamics, structure, origins.
From those potentially hazardous NEOs right here, close to home, all the way out to the icy remnants in the Kuiper Belt.
And we've already touched on those fantastic aha moments, haven't we? Discovering subtle things like the Yarkovsky effect nudging orbits.
Or the incredible detail coming from stellar occultations, all thanks to Gaia's precision.
It's really opening new windows.
And for you, our listener, if you are looking for that quick, thorough understanding of this really cutting-edge field, we genuinely hope this deep dive delivered that. Took you straight to the heart of Gaia's huge contribution to solar system science.
Yeah, hopefully a clear picture of why this mission is such a big deal for understanding planets and asteroids.
Which leads us to maybe a final thought for you to mull over.
Okay.
Given the, hundreds of thousands of objects Gaia is still going to observe, many totally unknown right now.
Yeah.
And the incredible level of detail it's revealing about the ones we thought we knew. What completely unexpected discoveries about how our solar system formed, how it evolved, might still be hiding in that data, what's just around the corner.
That is a compelling thought. Yeah. We know so much more, but Gaia is showing us there's likely much more we don't know yet. It's a really exciting time for planetary science.